So, in the last lecture we have discussed the Hanvenach theorem in details and all the form for the vector space, for complex vector in case of the complex vector space, and generalized form for a norm space, and so on. The next theorem which we will discuss today will be uniform boundedness theorem. As we have seen, or we have told already, there are 4 fundamental theorems: Hanvenach theorem, uniform boundedness theorem, open mapping theorem, and closed graph theorem. Hanvenach theorem does not require the completeness. It is simply we take a norm space or we take a metric space and an extension of the linear functionals are granted over the norm space with the help of Hanvenach theorem. But rest of the 3 theorems, that is uniform boundedness theorem, open mapping theorem, and closed graph theorem, requires the completeness of the space X. So, this also shows that the Banach space has a very important role in development of the functional analysis or in the theory of the functional analysis. A lot of application of this uniform boundedness theorem, open mapping theorem we can see in the subsequent topics of Banach theory of Banach spaces. The uniform boundedness theorem is basically uniform boundedness theorem this is basically done by S. Banach and H. Stenhouse. In 1927. This is also known as the Banach-Stenhouse theorem. Some authors say Banach-Stenhouse theorem, some books you can find the uniform boundedness theorem. The uniform boundedness theorem, the proof of this requires the category theorem. So, before going for this uniform boundedness theorem, we will discuss the category theorem and the related concepts of the category. So, basically we are interested in first discussing the Baires category theorem, and then subsequently we will prove for uniform boundedness theorem. To go for the category theorem, Baires category theorem, we require certain definitions or terminology for it. There are 2 types of terminology, one is the old one, another one the new one. So, we will use the old one inside the bracket and the new one as outside the bracket. So, we first discuss that category. A subset M of a metric space capital X D, a subset M of a metric space X D is said to be real. Is said to be real or nowhere dense set or nowhere dense in X. In X means XD. In XD, if its closure, that is M bar, has no interior point. That is the meaning is, suppose this is our a metric space XD and these are the elements of M. These are the elements of M. now this set, collection of this set is said to be real or nowhere dense set if the closure of this set has no interior point. It means if we draw an open bar around any point, then this open bar should not totally contained inside the closure M bar. Then such a set M is said to be a rare or nowhere dense set. Nowhere dense set is a old terminology and real is a new one. Similarly, we say meager a subset M of a metric space is said to be meager or of the first category. First category in X if M is the union of countably many sets each of which is real in X x t, real in x t. So, a set subset M of a metric space said to be meager or of the first category if M is the union of countably many sets each of which is real in x t. For example, if we pick up this set, say set of all rational number in R or in itself, set of all rational numbers in set of all rational numbers in R or in itself, in R or in itself. Okay. Set of all rational number in R or in itself. These two sets are of first category. Why? Because this is our real line, okay. Say real line minus infinity to infinity, here is 0. These are the points, okay, set of all rational numbers. So, M is the set of all rational number, M is the set of all rational numbers, okay, the set of all rational numbers. Now, you know the set of rational number are countable set. So, M is countable, okay. So, these are countable sets. Now, each one of these, if I take each of these, say x1, x2, x3 and so on, suppose I take and like this, then each one of this, closure of this is nothing but x1. So, each xi which is in rational number is a rational number. The closure of this is, I mean, union of countable which is there, okay, countable, and so let us set M is the set of rational, and the set X, that is R, is the closure of this, okay. R is the closure of this rational in R, whose closure is R. So, each of M is the union of the countable set. If M is the union of countable set, each of which is real in this. So, M can be written as union of xi, this set I is 1 to infinity. Now, each xi, this set is real in R or M or in M. because the closure of this, if you take any open interval, close this, it is not contained totally in M or totally in R, because in between the two rational there are the rational numbers also. So, we cannot choose like this. Okay. So, both are of first category, clear. Then this another definition is non-meager. Or of second category. Or of second category. In X, a subset M of a metric space is said to be non-meager or of second category in M X if M is not meager in X, meager in X, M is not meager in X. Okay. This is let it be this case. Okay. Okay. Not meager in A. So, if M can be expressed as a countable union of the sets union of this, and at least one of them has a that one of them has a non-empty open set, means interior point, then such a set will be a second category, all this. Okay. So, this type of set is of second. And we will prove that if a space is complete, then it will be non-meager in itself, or it will be the second category. Now, this is what we will show in the Baires category theorem. Okay. So, let us see the first result, the Baires category theorem. Category theorem. Okay. This is for a complete metric space. What this theorem says, if a metric space, if a metric space capital X which is non-empty is complete and is complete, then it is non-meager in itself, non-meager in itself. So, where categories theorem says that every complete metric space which is of course non-empty will be of second category. That is what. So, all the LP space they are of second category, L1 space etc. For example, LP space, L1 space, R and C and so on. These are all second category spaces. Okay. The same thing we can say as a consequence is we can also write this Baires category theorem in a more suitable form is that if X which is a non-empty set and is complete, and if X is a union of a cage, countable union of a cage where a cage are closed, then at least one AK contains a non-empty open subset. Non-empty. So, as a consequence of Baires category theorem, you can say that, or a more suitable form of the Baires category theorem is, if X if a complete metric space is represented by means of a countable union of AKs, where each AK is closed, then at least one of the AK must contain a non-empty open set subset. Okay? That is what we are. So, let us see the proof for it. Okay. So, we wanted to show this every complete metric space is of second category or non-meagle in itself. Suppose this is not true. Suppose a metric space which is non-empty and complete, but it is of first category. Then we should reach a contradiction, that is, we cannot be able to write X in the form of this where one of these AKs contains a non-empty intersection. Okay? Let us see. The idea of the proof is, suppose the metric space, suppose the metric space X which is non-empty is of first category. In itself, first category in itself. It means X can be represented as the countable union of MKs, countable union of MK, where each MK is real in X, where each MK is real in X, is of first category. Okay? It is real in X. It means the closure of this, it does not contain any interior point. That is what it is. Now, we will show this as a contradiction, that is, we cannot be able to express X as a countable union of MK, where each MK countable union of MK, where each MK is real unless X is not complete. Okay. So, when we say X is not empty, okay, X is then and is of first category, then we will reach certain contradiction. Okay. Let us see how. So, the proof is like this: we will construct a Cauchy sequence in M, and since the M is complete, so its Cauchy sequence must converge to a point in M, and that point if it does not belongs to any one of the MK, okay, and that limit point belongs to A because X is complete. So, if that point does not belongs to MK, then X cannot be represented into this form. So, that is the idea of the proof. Okay. So, let us suppose since M1 is real in X, which is a complete metric space. So, by definition M1 closure does not contain a non-empty open set. So, by definition M1 closure does not contain a non-empty open set. Okay. Because M1 is real. So, this is our X and this is our M1. So, because it is real, it means by definition of the real, a set is set, a subset M of a metric space is said to be real if each of its point does not contain any, if the closure of this does not contain an interior point. So, that is why M1 closure does not contain an interior point, means it will not contain any open sets in it. Okay. What X is giving to be complete is complete. So, M1 XD is complete, therefore, if we take any and M1 does not contain. Okay. So, since M1 X is complete, so every Cauchy sequence is convergent. It means the limit point belongs to it. So, it will have an open set which is totally contained inside it. Therefore, since X will complete, so it will contain a non-empty open set. Okay. So, it will contain non-empty open set. Contain a non-empty open set at some point. Okay. Now, since our M1 closure does not contain a non-empty open set, but XD is complete contains a non-empty, it means M1 closure cannot be X. So, M1 closure is not equal to X. Okay. So, there will be some complement for it. So, this is our M1 closure, this is the M1 closure. Okay. Now, this M1 closure will contain the some open set. So, M1 closure of this will be X minus M1 and of the M1 wall is not empty, and so M1 which is non-empty, obviously because this contains some point X and this M1 closure is a subset of X and open. Okay. So, M1 closure is this. Say I am just putting here, say this is our M1 closure, just as. So, this is a non-empty and open set. It means at some point we can find. So, if P1 belongs to is, so B may, so at choose the point since it is non-empty. So, at the point P1 which is in M1 closure, one can find an open ball which is totally contained inside it. So, at the point P1 which is in M1 closure, we can get a open ball, say B1 centered at P1 with a radius say epsilon 1, which is totally contained in the M1 closure, and let us suppose epsilon 1 is less than say half. Okay. Now, since this M1 closure is an open set, non-empty and open, so we can find out an open ball around this with a radius say epsilon 1, which is totally contained in the M1 closure. Okay. So, this is one. Now, further M2 is again real in X, M2 is real in X, so that closure of this M2 closure does not contain, by definition, does not contain any non-empty open set, does not contain a non-empty open set. Clear? Okay. So, if it does not contain an open set, it cannot contain the open wall this. So, hence it does not contain open ball B say centered at P1 with a radius say epsilon 1 by 2. Okay? Because it does not contain any non-empty open set. So, obviously, it will not contain the ball centered at P 1 with a radius less than epsilon by 2, but its closure will contain the open ball. So, this implies that the closure of this M2 closure intersection with this B open ball B 1 with epsilon by 2, the closure of this is not empty. Okay? And open, and it will be an open set, and open, because M2 does not contain. So, closure of this x minus M2 again is an open set and non-empty, and since this ball is not contained inside. So, intersection part will remain open and non-empty. Okay. So, it will have certain, so we may choose, so that we may choose, so we can choose, because it is non-empty, an open wall in this set. Say B 2, which is centered at P 2 with a radius say epsilon 2, which is contained in M2 wall closure intersection the ball P 1 epsilon by 2, and epsilon 2 is less than half 2 square. Say epsilon 2 is less than half of epsilon 1, but epsilon 1 is already less than half. So, basically this is less than 1 by 2 square. Okay. This is, so we can get the open wall. It means this is our, if we draw the bigger figure, this is say M1 closure. Here we are getting P1 and this wall say B1. Okay. Then what we get it is the P1 with the radius epsilon by 2, we are drawing a ball B2. This is our B centered P1 and radius epsilon by 2. So, B centered P1 radius epsilon by 2. Now, this ball and intersection with M2 closure will be non-empty. So, there will be a point P2 and we can draw the ball around this point Pt with a radius less than 1 by 2 square, then it is totally contained inside it. That is why. Okay. So, continue this process. So, continue this. Okay. So, by induction we can say, by induction we thus obtain a sequence of balls say B case with centered P k and radius say epsilon k, where each epsilon k, where epsilon k is less than half to the power 2 k, such that the intersection with M k is non-empty and it is an open set, and the next ball B k plus 1 will contain inside the B k, inside this B k, that is in fact it will contain between B P k B k plus 1 is contained in ball B centered at P k with a radius epsilon k by 2, which is contained in B k. Okay. So, the B k plus 1 is contained in this. That is what, and k is, this k is 1 2 3. So, by induction we are getting slowly the balls inside this closures, and B1, B2, Bn all the sequences of the balls which has a center P1, P2, Pn. Okay. So, we are getting the sequence Pk. Now, we are getting sequence Pk as the centers of the walls, okay, centers of walls such that this holds, say star holds. So, we can say that, and where epsilon k is less than 2 to the power minus k. So, this is going slowly to 0. It means this sequence of the center. So, the sequence Pk of centers is a Cauchy sequence. Okay. Cauchy sequence in X, but X is complete. So, this Cauchy sequence will converge. So, this sequence Pk will converge to say P belongs to X, will converge to P because it is complete. Therefore, this point P will be the limiting point of all Pk. Okay. Limiting point of P. Now, the distance between Pk and P under this will also go to 0 as m tends to infinity. That is, P will be the limit point of this. That is what we want. Okay. Because the reason is for every m and n greater than m, we have Bn is contained in B with center Pm and radius say epsilon m by 2. So, that the distance between Pm and P will remain less than or equal to say epsilon m by 2. Why? Because this is less than equal to Pm Pn plus d of by triangular inequality Pn P. Now, this is less than epsilon m by 2 because of Pm is the center and Pn belongs to it, and that this distance Pn P it goes to 0 because of this. So, this total will go to epsilon m by 2. It means the P is the center, okay, and Pm is a point belonging less than epsilon m by 2. So, it belongs to the class P belongs to the ball Bm, and this is true for every m. Okay. But Bm is contained in the Bm is contained in the complement part of the closure of mm. So, what it says, if P belongs to Bm and Bm is in this, so P will be the point in the complement part of mm closure, but it means it cannot belongs to the mm for any m. So, this implies hence P does not belongs to mm for every m, Okay. Therefore, P is not the point in the union of m. But as our assumption is this is x, okay, by our assumption. Therefore, and x is a complete matrix where x belongs to this class, here P belongs to this class, where the P does not belongs to this. So, these two will reads say alpha and beta will give a contradiction. Okay. Then this contradiction is reached because of a wrong assumption that the set is of first is not of second category. Therefore, the space M which we have discussed earlier, assume this one, that is we assume this is the metric space is of first category is wrong. Therefore, space X D will be of second category, will be of second category, and this proves category theorem. Okay. So, this one. So, every complete metric space is of second category, but it does not mean the incomplete metric is not of second category. The converse of the Baires category theorem is not true. That is, if a set is of second category, can you say it will always be a complete metric space? No, it is not true always. It is not true. In fact, there are incomplete metric spaces, incomplete norm spaces, in fact, incomplete metric space which is non-meager, and this is shown by Bourbaki in his book X7 third 4. He has chosen an incomplete norm space where he has shown incomplete norm space which is of second category. Okay. This is a detailed exercise, so you can go through. Okay. So, that is okay. Now, once we complete this category theorem, then base is developed to prove our uniform boundedness theorem. So, let us see the next result is the uniform boundedness theorem. This is also known as the Banach-Steinhaus theorem. What this theorem says is, let the sequence Tn be a sequence of bounded linear operators from Banach space X to a norm space by, from Banach space X into a norm space by. X to be Banach and by need not be a Banach, such that the norm the sequence of the norm T n x is bounded for every x belonging to capital. It means corresponding to x we can find a constant c such that norm of T n x remains less than or equal to c. That is norm of T n x is less than or equal to c suffix x. Suffix means it depends on this, which is a real number. Okay. This is a constant, real constant, depends on x. Okay. Depends on x, is a real number. So, a sequence of a bounded linear operators are given from a Banach space to a norm space, which is pointwise bounded. That is, sequence of the norm operators are pointwise bounded. Then what this theorem says is, then the sequence of the norm Tn is bounded. That is, there is a C, there exists a real number C independent of x such that norm of Tn is less than or equal to C. Now, and n for all n 1 to 3. So, what this theorem says is, in short we can say, the result says that pointwise boundedness implies the uniform boundedness. That is, in case of the pointwise boundedness of the operator Tn from x to y, x is Banach and this is norm, is uniformly bounded. That is what the result says. Okay? Pointwise boundedness implies the uniform boundedness if x is a complete norm space and y. Okay? So, let us see the proof for it. The proof will depend on the category theorem, Baires category. We will make use of Baires category theorem to prove these results. So, what we do is, we will first find out the closed set, and then we say that x is union of the closed set, and if x is complete already, then by Baires category theorem it will have a certain open subsets, some subset which is non-empty and contains the sequence, means open. Okay? So, that is the one. So, let us see for each k natural number belongs to n, let us consider a k which is contained in x and be the set of all x such that norm of Tnx is less than or equal to k for each n for all n. Okay? Means a k is the set of those x belonging to capital X such that under the image of this is bounded by k. Okay? For each n. T1x is less than or equal to k, T2x is less than or equal to Tnx. Now, we claim that ak is closed. Okay? So, all the limit point belongs to it. So, let us take x belongs to, consider x belongs to, since the reason I am giving, since if we take x belongs to the ak closure, then by definition there will be, since a, so there exists a sequence, xj in ak converging to this x, because ak closure, this is the limit point I am choosing. So, there will be a sequence in ak closure xj in ak which tends to x under the same norm of this x. Okay? It means for xj, since xj belongs to this, since xj belongs to ak, so for every fixed n, we have the norm of Tn xj is less than or equal to k by the property of ak. If xn j belongs to this, then T n x will be less than or equal to k for each n. So, let us fix the n and get it. Once you fix n, now let j tends to infinity, let j tends to infinity. So, let j tends to infinity. Okay. Now, this implies norm of T n x is less than or equal to k, because norm is a continuous function and T n's are given to be a operators. So, when limit you take, limit will come inside and it will give the limit of x j, which is equal to j. So, it will. Okay. So, this shows norm is continuous and T n is also continuous, because it is a bounded linear operators. T n is also continuous. So, because of this thing we can get. Therefore, this implies that x belongs to a k. So, a k is closed and for each k. Okay, this k. Now, once a k is closed, then we can write down this. Take any x belongs to capital X, it will belongs to one of the a k's. Okay. Therefore, since norm of T n x is less than or equal to C x is given. Okay. Therefore, each of x, therefore, each x which is in X will satisfy this condition. It means it will belongs to any one of the a k's. So, belongs to some a k because of this property. Okay. So, x can be expressed as a union of this. So, x can be written as a union of a k, k is 1 to infinity, countable union of this. Clear? This all. So, we have x, we have an arc space, we have proved that this x can be expressed as a countable union of a k, where a k satisfies this condition, which is a closed set. Okay. Now, apply the Baires category theorem. If x is complete, then by the Baires category theorem, this representation means one of the a k will contain the open ball centered at x naught and radius suitable radius. So, since x is complete, okay. So, by Baires theorem, category theorem, we have some a k which contains an open ball, say B naught, which centered at x naught and radius say r, which is contained in a k naught. Okay. Some of these a k, say a k naught, contains an open ball B naught with radius a naught. Okay. Now, let us take an x arbitrary point. Arbitrary and different from 0. Okay, different from 0. Now, consider the point z, which is x naught plus gamma of x, where gamma is a constant term, gamma is say r over 2 norm of x, because x is already given. So, we can find out the norm of x. So, this becomes a real quantity. So, z, which is x naught plus gamma x naught. Now, this has a property. Okay. Consider them. Now, if I take z minus x naught, norm of this, then this becomes gamma into norm of x, but gamma is r by 2 norm of x into norm of x. So, this is equal to r by 2, which is less than r. It means that a ball centered at x naught with a radius r contains z. So, this belongs to B naught. So, z belongs to B naught, okay, by definition. And further, because the z belongs to B naught, and what is B naught? B naught is this open valve which is contained in A k naught, which is contained in A k naught. So, z will satisfy the condition that norm of this T n x naught is less than or equal to k naught T n z. So, this implies the norm of T n z is less than or equal to k naught for all n, for all n. Okay, that is what it is. Further, norm of T n x naught, this is also less than or equal to k naught. Why? Since x naught is the center of B naught, x naught is the center of B naught and belongs to B naught. So, B naught, therefore, again by the same property B naught is a subset of A k naught. So, we can get this. Therefore, we can get from here, this implies that norm of T n x, which is equal to 1 by gamma norm of T n x means z minus x naught. Okay. Now, this will be equal to less than or equal to 1 by gamma norm of T n z plus norm of T n x naught within bracket. Now, T n z naught, gamma is this, gamma is r by 2, 1 by r means it is 2 norm x by r, and this is less than or equal to, because each one is less than k naught. So, this is 2 k naught. So, what we get is that 2 k naught, and this will be 4 by r into norm of x into k naught. Okay. So, this will be equal to this. Now, this, therefore, supremum of this divide by norm x, when x belongs to the x and norm of x is 1, then this supremum is bounded by 4 by r k naught, which is some constant c. There, but this supremum is norm. So, norm of T n is less than or equal to c for all, and this completes the proof. Okay. So, we can get this. Is it clear now? So, we have proved this uniform boundedness. We can directly use this uniform boundedness theorem as an application. One can solve many problems for this. So, first let us see the one application where this uniform boundedness theorem has used. So, let us take the one exercise. The norm space X of all polynomials with norm defined by norm of x is maximum of mod alpha j over j, where alpha naught, alpha 1, alpha 2, alpha are the coefficients of x is not complete. So, what we do is we will generate a bounded linear function on x, which is pointwise bounded, but not uniform bounded. So, this by Baires category theorem you can say it is not complete, that is all. Okay. So, let us consider an x, a polynomial x which is not 0 of degree n or nx. So, we can write x in the form of sigma j equal to 0 to infinity alpha j t j, where the alpha j 0 for all j greater than n x. Okay? Then and define T n as our f n sequence of linear functional such that by this f n 0 is 0 and f n x is sum of this alpha 1 alpha 2 alpha n minus 1. So that we can see from here clearly T n, which is say f n, are linear and bounded. Why bounded? Because mod of alpha j is less than equal to norm x, because the maximum is there. Therefore, this each one f n will be a bounded function. So, mod of f n x, so mod of f n x, this will remain less than equal to sum of this n x into maximum of mod alpha j where j, and this is nothing but a c x. So, it is pointwise bounded, but norm of f n is not bounded, because but f n x, but if we take x t to be 1 plus t square plus t to the power say n, then norm of x becomes n and f n x, this x becomes 1 plus 1 plus 1 up to n. So, n into norm x, therefore, norm of f is equal to n. Norm of f is greater than equal to mod f n x over norm x, and mod f n x is n. So, this will be n into norm x, we can write it, is it not? So, this is equal to n. So, it is unbounded. Therefore, by uniform boundedness theorem, x cannot be complete, and that is what we want to show. Okay? Because it is pointwise bounded, but it is not uniform bounded. Therefore, this x cannot be complete, because if it is complete, it must be bounded. Thank you. Thanks. Okay. Here and this one.